Welcome back to Calculus 3. I'm Dr. Jeff Groh. Today we're going to talk about Green's theorem. First, I need to make some definitions. The set R is called path-connected if for every points A and B that live in the set R, there exists a path C between the points A and B, where the path C remains in the set R. So, for example, suppose I give you a set maybe that looks like this. This set is path connected because between every 2 points you can find a path, and the path stays within the set R. However, a set like this is not path connected because you can find 2 points and no path between those 2 points stays within the set. It has to leave. Sets that are path connected can be fairly complicated sets. But as long as between every pair of points you can find a path that stays within that set, it is path connected. Also, if this is a region R, we say that a curve is homotopic to a point if there is a continuous sequence of curves that can be contracted to that point. Also, given some region R, we say that a curve that is closed, that means it begins and ends at the same point, it forms a loop. We say that this curve is homotopic to a point within R if there's a sequence of curves, a continuous deformation of curves that contract the curve to a point where each of the intervening curves is within R. As an example of a curve that is not homotopic to a point within some particular set, consider the region R and it has a hole in it like this. If you take a loop around the hole, then whenever you contract this continuously to a point, you have to pass through points that are not in the region R. So because these intervening loops leave the region R, at least on some points, we say that the original loop is not homotopic to a point within the set R. As another example, consider points on the surface of a torus. If you have a closed loop that goes around the torus like this, and you try to contract it in any way to a point, you have to pass outside of the surface of the torus. It has these closed loops that are not homotopic to a point within that surface. The same is true for loops that go around the other way. Let's try that again. I don't know if I got that right. The region R in the plane R2 is called simply connected if first it is path connected So it can't be like this. Path-connected sets if it is path-connected and every closed loop in R is homotopic to a point in R. In other words, it can't have holes. An example might be a region like this is not simply connected because if I have a closed loop that goes around the hole, whenever I try to contract that to a point, these intervening loops will have to leave the region in that process. The punctured plane is also an example of a space that is not simply connected. Any loop that goes around the hole in the plane, when you try to contract it back to the origin, will have to go through that hole and hence leave the set. We sometimes think of simply connected sets as being those that have a boundary that is a single, simple, closed curve. The curve is closed if it begins and ends at the same place. It's simply closed if it doesn't do this. It doesn't have double points like this. So it can't intersect itself if it's a simple closed curve. A region with a hole in it has two boundary curves, curve 1 and curve 2. However, the region outside of this hole has one single simple closed curve as its boundary, and yet this region is obviously not simply connected because we can take loops around the hole, and again, when contracting them back to a point, the intervening curves will have to leave the region and pass through the hole. So just describing a region having a single simple closed boundary curve is not enough to describe what we mean by simply connected. We're ready for Green's theorem. Let R be a simply connected region in the plane with the boundary of R a single simple closed piecewise smooth curve. So we're assuming here that the region R has a single simple closed boundary curve. We're going to orient the curve in a counterclockwise fashion so that if you were to walk in the direction of the tangent vector to the curve at each point and stick your left arm out, your left arm will be pointing into the region R. So we're going to orient the boundary curve in a counterclockwise fashion. We're going to let the functions m and n, which are going to be defined, not only on R, but they're going to be defined on some open set that contains both R and its boundary. So some open set that surrounds the whole thing. Let these be C1. So not only are these continuous functions, they're differentiable and have continuous partial derivatives. on an open set containing R and the boundary of R. Then it turns out there are three versions of Green's theorem, and I want you to know all of them. In the first version, we do the integral around the boundary of the region. Notice this is an integral on a closed loop. We're integrating m dx plus n dy. The theorem asserts that instead of integrating this differential form, we call this a one form, m dx plus n dy, around the boundary, you may do the following instead. For emphasis, I'll put a double integral here, but it's obvious that it will be a double integral because we'll have an area element. What you'll do is you'll integrate the partial derivative of n with respect to x minus the partial derivative of m with respect to y up against an area element. Now, I know that this is going to be a challenge, remembering which partial derivative goes with which of these two functions, but I'm going to give you a little special tool in a few minutes to help you remember what goes where. The second version of Green's theorem is the Flux version. Remember, you have your little region R. The boundary is this curve which we're orienting in a counterclockwise fashion. If at each point of that boundary curve we have a unit exterior normal, then we can calculate the flux by integrating around the boundary of the region F, where I'm assuming here that the vector field F is Mn dot n ds, element of arc length, is equal to, and again, unnecessary to write the double integral, but I'll do it for emphasis anyway, of the divergence of F across that whole region. For the first time, we'll be able to connect this notion of flux, vectors' tendency to go out of a region, and the divergence, which is a measure of a vector field to diverge apart at each point. It's really kind of fascinating that to calculate the flux, we're only measuring the tendency of vectors at the boundary to cross across that boundary. This is the flux. We can equivalently calculate the flux by integrating across the entire interior of the region, the divergence. In other words, the divergence is a form of flux density. It's the flux per unit area multiplied by an element of area and added up gives you the total flux. The third version is the circulation version. Recall that you calculate the circulation of a vector field in a region by calculating f dot dr. And again, for emphasis, we'll put the double integral on the right-hand side. That's going to be equal to the curl of f dot k dA. This is sometimes called Stokes' theorem in the plane, for reasons that will become obvious after we discuss Stokes' theorem. However, again, notice the curl, at least if the vector field is in the plane and it has a non-zero curl, then the curl will be pointing in the direction of the z-axis. So dotting by k gives you the magnitude of that and the orientation. If you take your curl, which in the plane would be only in the z-axis direction, only in the k direction, if it's rotating in a counterclockwise fashion in the plane, you'll have a positive dot product here. And so you'll get a positive circulation. If it's going in the other direction, you'll get a negative for the dot product. And so a negative circulation going the other way. It's kind of fascinating then that the circulation, the total circulation, can be found by integrating across the entire interior of the region this curl dot k. In other words, the curl represents a circulation density. Before proceeding to a proof, I would like to teach you something that will help you to remember the first version of Green's theorem that we wrote down. It's something called the wedge product. Yes, I'm going to give you a wedgie, and you're going to love it. You'll say, "Thank you, sir. May I have another?" First, let me define what I mean by a one-form. One-forms in the plane are going to be functions that look like this: a function of x and y times dx, and a function of x and y times dy. Now, we're going to define a wedge product on the differentials. dx wedge dx will be 0. dx wedge dy will be minus dy wedge dx. In other words, just like the cross product, the wedge product is going to be skew symmetric. Of course, if it is skew symmetric, then dy wedge dy is also 0. Now I need to define what I mean by the differential of a one-form. If phi is m dx plus n dy, then d phi will be calculated as follows. You'll calculate dm dx dx plus dm dy dy. That's the usual differential of the function m, but you're going to take the wedge product with dx plus the differential of n, dn dx dx plus dn dy dy, and you're going to wedge with dy. Now, when we do this wedge product, the wedge product will be able to distribute across sums like this. We'll end up with a dx wedge dx. So that first term will go away. On the second term, we'll have a dy wedge dx. Remember, the wedge product is skew symmetric. To reverse that, we'll get minus dm dy dx wedge dy. And then on the next term, we'll get plus dn dx dx wedge dy, and then 0. Rearranging these terms, we have d phi is dn dx minus dm dy dx wedge dy, and this is exactly in the form that we need for Green's theorem. You'll recall that for Green's theorem, we're integrating m dx plus n dy. You'll get the integral over r of, you take the derivative of n with respect to x, because that gives you a dx wedge dy. When you take the derivative of m, if you took the derivative with respect to x, you would get a dx wedge dx, but that's going to be 0. The only derivative here that will survive is dm dy, but when you put a dm dy in here, you'll have dy wedge dx, which has to be reversed in order to combine the two terms. That generates a minus sign. dx dy, which is the same thing as the element of area in the plane. You can always get from here to here by thinking about the wedge product. You take the derivative of m with respect to y. You get a dy wedge dx, which has to be reversed, and that gives you a minus sign. You take the derivative of n with respect to the other variable, x, that gives you dn dx. So you never actually have to calculate the differential of the one form again the way that we did, because you can always figure out what derivative to take on which of these functions, m or n, and which one gets the minus by thinking about the wedge product. I should also mention that there's a more general version of Green's theorem that is expressed in terms of one forms and these differentials, including the wedge product. This version of Green's theorem can be generalized to cover all of the rest of the integral theorems from here to the end of the course. The major theorems are Green's theorem, Gauss's divergence theorem, and Stokes's theorem. Each of these theorems looks different, but they can all be expressed as a special form of a more general theorem called the generalized Stokes theorem. We have three versions of Green's theorem. We have the one-form version, we have the Flux version, and we have the circulation version. I would like to prove all of these, but we're going to prove the first version, and we're also going to prove that the other two are implied by the first version. That hinges everything on proving the first one. We're going to prove first that 1 is equivalent to 2, and also that version 1 is equivalent to 3. That will hinge everything on our ability to prove the first version. Then we'll prove that version separately. So in our proof, 1 is true if and only if 3 is true. We'll prove the equivalence of 1 and 3 first. We'll let the vector field F be m, n. Then the left-hand side is the left-hand side of the first version. After all, dr is dx dy. All we have to do is verify that the right-hand side of the third version corresponds to the right-hand side of the first version. To do that, we need to calculate the curl of our vector field. Keep in mind that our vector field has coordinates that are functions of x and y only, no z's. This vector field lies entirely in the xy plane and is unaffected by the variable z at all. So when we calculate the curl, we'll get 0 minus 0 because n does not depend upon z. And then 0 minus 0. The only part that's not 0 is the derivative of n with respect to x minus the derivative of m with respect to y. You can see now that when you dot with k, you'll pick out this last coordinate, and that will give you the right-hand side. Next, we'll prove that 1 and 2 are equivalent. In this case, we'll set F to be the vector field n, comma, minus m. In this case, the divergence of F will be the derivative of n with respect to x minus the derivative of m with respect to y. It follows then that the integral on R of the divergence of F dA will be the integral on R of dn dx minus dm dy dA, verifying that the right-hand side of 2 is the same as the right-hand side of 1. We just need to prove the left-hand sides are also equivalent. First, recall that if I give you a vector AB and I want to find a vector that's orthogonal to it, I can just reverse the coordinates and negate one. The dot product will be AB minus AB, which gives me 0. Also recall that the unit tangent vector is the derivative of the position with respect to arc length. That's going to be dx ds, comma, dy ds. The unit exterior normal is the same length, 1, but it's at a right angle. So what is the unit exterior normal? Well, how about dy ds, comma, minus dx ds? Reverse the coordinates and negate one. You just better make sure it's not the interior normal instead. Notice that with the tangent vector that we have depicted here, the x-coordinate is negative and the y-coordinate is positive. So dx ds will be negative and dy ds is positive. The exterior normal has both positive coordinates. So dy ds is positive and negative of a negative is positive. So this is the correct place to put the minus sign. Also then, the integral around the boundary of the region of f, which we said was n minus m dot n, that's dy ds minus dx ds ds, will be the integral around the boundary of R of n dy and then minus m dx. Since we have proven that 1 is equivalent to 2 and also that 1 is equivalent to 3, we really only need to prove 1. To do this, we're going to break this into 2 parts. We're going to show, first, that the integral around the boundary of the region of m dx is the integral on R of minus dm dy dA. We'll do this in 2 parts. Suppose we have our region R like this. Here's what we'll do. We'll slice and dice this up into little subregions. We'll make a partition. And we'll have little subregions R sub k. Each of those little subregions has its own boundary. Here's what we'll do. We'll choose sampling points, C sub k, within each of these little regions, and we'll look at the Taylor expansion. Do you remember Taylor series? A function f is a function at x naught plus f prime at x naught times x minus x naught plus higher order terms. In multivariable cases, it was a little different. In the multivariable case, we had m of x is equal to m of ck plus the derivative of m with respect to x at ck, where if ck has coordinates c1 and c2, we'll have x minus c1 plus dm dy at ck times y minus c2 plus higher order terms. Yes, this will be our Taylor expansion. Now, what we'll do is we'll note that if we're integrating around the boundary of R, m dx, you'll get the same thing if you take the sum as k goes from 1 to n and integrate around the boundary of the R sub k's. Now, why is that true? That follows because of something called the cancellation principle. As we're going around these little cells, we have to go around them in a counterclockwise fashion. But on an adjacent cell, we'll be going in exactly the opposite direction. So if we integrate around all of these little cells, we'll be going around each little boundary piece on the interior twice, but in opposite directions. And when you switch directions on an integral of this type, it changes the sign. So the integrals on all of the little interior boundary pieces will cancel. That means the only thing left will be the integral around the actual boundary of the region R. So these two must be equal. So the integral around the boundary of R of m dx is the sum, as k goes from 1 to n, of the integral around the boundary of the R sub k's, m dx, but because of Taylor's theorem, that's the sum, as k goes from 1 to n, of the integral around the boundary of the R sub k's of m evaluated at c sub k plus dm dx at c sub k times x minus c1k plus dm dy evaluated at ck times y minus c2k plus higher order terms, to all times dx. Now let's think about this. Here I have m evaluated at ck. It's being multiplied by the differential dx, and I'm integrating in a closed loop. This is a constant. You know that if you integrate dx in a closed loop, you get 0, because the sum of the little changes in x in a closed loop is 0. So the first term gives you nothing. The second term is a function of x alone. The partial derivative of m with respect to x evaluated at ck is a constant times a function of x. If you integrate any function of x times dx on a closed loop, you get 0. We proved that because any such function represents something that arises from a conservative vector field. Closed loop integrals gives you nothing. On the next term, when we distribute the partial derivative to the second term, you get a constant up against a dx. That gives you nothing. The only term that contributes anything to this integral will be the partial derivative of m with respect to y evaluated at ck times y dx. This is a constant times y dx. What do you get if you integrate y dx around a closed loop? You get minus the area. So we have the sum, as k goes from 1 to n, of the following: dm dy evaluated at ck times minus the area of rk. This is minus a little delta A sub k, a little change in area for each of these little pieces in the partition. If we take these and add them up, and then take the limit as these little delta A sub k's go to 0, we will get a double integral. We'll get minus the double integral over the entire region, of dm dy times the element of area. That completes the proof of the first part. Now we also must show that when we integrate around the boundary of r of n dy, what we get is the integral on r of dn dx dA. Not minus, but plus this time. Let's think about why that should be so. We'll partition the region just like before and express this as the sum as k goes from 1 to n of the integral around the boundary of the r sub k's of n dy. And we'll use Taylor's theorem just like before. We'll have n evaluated at the ck's, dn dx at ck times x minus c1k plus dn dy at ck times y minus c2k plus higher order terms, all times dy. A constant up against the dy on a closed loop gives you nothing. The function of y on a closed loop should also contribute nothing. This constant term will contribute nothing. The only thing that will contribute something is the x dy, and that gives you a little element of area. So we'll have the sum, as k goes from 1 to n, of dn dx at ck times this little element of area. In the limit, as these little elements of area go to 0, we end up with exactly the integral on r of positive dn dx dA. Let's find the work done by the force field F equals y cubed I plus x cubed plus 3xy squared j in moving a particle on the path three cosine t, 3 sine t, where t goes from 0 to 2 pi. In other words, we're going to go on the circle of radius 3, and we'll go in this orientation. In this case, we can view a region R to be the disk of radius 3, whereas the boundary of the disk is the circle of radius 3. Recall that the work is the integral along the path of f dot dr. We have then that the work will be, in this case, because we're dealing with a little closed loop, integral around the boundary of the disk of radius 3 of f dot dr. That's going to be y cubed dx plus x cubed plus 3xy squared dy. According to Green's theorem, this should give you the same thing as the integral on the entire disk of radius 3 of the derivative of n with respect to x minus the derivative of m with respect to y. To set this up, since we're integrating over a disk of radius 3, we should use polar coordinates. 3x squared is going to be 3r squared cosine squared theta. The element of area is r dr d theta. You can see we'll get the integral from 0 to 2 pi. We have 3r cubed. That's going to be 3r to the 4th over 4, evaluated from 0 to 3. Cosine squared we will convert to 1/2 1 plus cosine of 2 theta. We'll have 3 to the 4th, which is 81, times 3 is 243 over 8. And then we're integrating cosine 2 theta from 0 to 2 pi. The period of this function is 2 pi over 2, which is pi. So if we integrate over 2 periods, we get doubly nothing. Integrating 1 on an interval of length 2 pi gives me a factor of 2 pi. So the answer is 243 pi over 4. We calculated the path integral, the total work done in moving a particle on this closed loop, by converting to an area integral using Green's theorem. We could have evaluated the work integral directly by parameterizing the boundary curve and then just substituting into the line element. Let's do it that way too, to verify that you get the same thing on each side of Green's theorem. We started off with y cubed dx plus the quantity x cubed plus 3x y squared times dy integrated around a circle of radius 3. Our parameterization is, of course, 3 cosine t, 3 sine t. You cannot write 3 sine t and then 3 cosine t because that gives you the wrong orientation. We're going to presume that always you keep the curve oriented in a counterclockwise fashion as you go around it. So if you're walking along the boundary and sticking out your left arm will poke into the region that's contained within the boundary curve. Substituting, we have the integral from 0 to 2 pi. Y cubed will be 27 sine cubed times dx. Dx will be minus 3 times sine times dt. We'll have 27 cosine cubed. 3 times another 9 gives me 81. Times cosine times sine squared. And then we get 3 cosine dt for the dy. We have an 81 here. And when we distribute the 3, we'll have an 81 everywhere else. We can bring an 81 out. That brings an 81 out of the entire integral. Let's see what's left. The dt can be factored out of everything. We'll have a cosine to the 4th minus sine to the 4th, and then plus 3 cosine squared sine squared all times dt. Cosine to the 4th minus sine to the 4th is a difference of squares. It's cosine squared minus sine squared times cosine squared plus sine squared. Well, the plus part is the Pythagorean identity. But cosine squared t minus sine squared t is the double angle identity for cosine. Also, we have this cosine t sine t looking over here. You'll recall that the sine of 2t is twice the sine of t cosine of t. If we divide the 2 off and then square, we'll have 81, the integral from 0 to 2 pi, the cosine of 2t plus 3/4 sine squared of 2t dt. Cosine 2t has a period of pi, and we're integrating over 2 periods. So the first term contributes nothing. For the second part, we use a half-angle identity. So far we have a 3/4. We're going to multiply by 1/2 times the quantity 1 plus the cosine of 4t. The cosine of 4t will contribute nothing. The period is pi over 2. So we're integrating over 4 periods. That gives you quadruply nothing. And so we end up with 1 integrated from 0 to 2 pi, which is 2 pi, times all of the other constants. We'll have 243 divided by 8 times 2 pi, or 243 pi over 4. Exactly the same answer we had by using Green's theorem and using an area integral instead of this path integral. Now, I want you to be able to do these integrals both ways. You need to be able to do both the path integral on the left-hand side of Green's theorem and the area integral on the right-hand side of Green's theorem. You can be quite sure that the first problem on the final exam will be verify Green's theorem for a particular problem. And when I say verify, I don't mean prove Green's theorem. We've already done that. Instead, what I mean is check the integral, the path integral on the left, check the area integral on the right, and verify that you get the same answer. In our next problem, I want to verify Green's theorem we'll be integrating around the boundary of some region y dx plus x squared dy, where the region is as follows. We're going to go from 0, 0 to the point 1, 1 along the curve y equals x squared, and then we're going to go straight back along y equals x. That's going to be the boundary of the region. The region R is the region in between these two curves. We need to verify Green's theorem, so we're going to have to do both the left-hand side, the path integral part, and the right-hand side, the area integral part. Let's do the right-hand side first. On all of these problems where I ask you to verify Green's theorem, or Gauss's divergence theorem, or Stokes's theorem, I want you to state the theorem. On the final exam, when I ask you to verify Green's theorem, the first thing I want you to do is to state at least the equation involved in Green's theorem. So Green's theorem is stated in terms of a formula as the integral around the boundary of region R, n dx plus n dy is the integral on R of dn dx minus dm dy dA. You'll at least get 3 points on the problem in the exam if you make this statement. Remember, we're trying to calculate the integral around the boundary of the region of y dx plus x squared dy. Let's do the right-hand side. RHS stands for right-hand side of Green's theorem. We have dn dx minus dm dy. If we use vertical cross sections, x values will be integrated from 0 to 1, and the y values will go from the lower curve to the upper curve, from y equals x squared to y equals x. The integrand does not involve y, so we'll have the integral from 0 to 1 of the integrand times the length of the interval. The highest degree term that you get when foiling is a negative 2x cubed. You'll also get a positive 2x squared and another positive x squared. That's plus 3x squared. And now the lowest degree term is minus x. Using the fundamental theorem of calculus, we get minus x to the fourth over 2 plus x cubed minus x squared over 2, evaluated from 0 to 1. Plugging in the 1, we get minus 1/2 plus 1 minus 1/2, and that's 0. Let's check that we also get 0 on the left-hand side. On the left-hand side, the boundary of the region can be decomposed into two curves, curve 1 and curve 2. On curve 1, we'll parameterize it as t squared, where t goes from 0 to 1. So the integral on curve 1 will be the integral from 0 to 1 of y times dx plus x squared times dy. That's going to be t cubed over 3 plus 2t to the fourth over 4, evaluated from 0 to 1. That's 1/3 plus 1/2. Now, curve 2. Negative curve 2 goes in the opposite orientation. We can describe it as t, where t runs from 0 to 1. So the integral on C2 will be minus the integral on minus C2, and that's minus the integral from 0 to 1 of y dx plus x squared dy. This gives us then minus t squared over 2 plus t cubed over 3, evaluated from 0 to 1, or minus 1/2 plus 1/3. Adding that to the previous results, we get a total of 0. The boundary integral will be the integral on C1 plus the integral on C2, and we've seen that that has a sum exactly equal to 0. This verifies that Green's theorem is true. Suppose that we have a region that has a great big hole in it, in which case the Green's theorem that we've presented doesn't apply because the region is not simply connected. Is there a way to force it so that we can get Green's theorem to work anyway? The answer is yes, or else I wouldn't have brought it up. It goes like this. Suppose that you start off traveling around the boundary, and you get to some point, and then you make a little cut. I'm going to go this way inside. We'll go this way first. We're going to make a turn and go to the middle. And this little cut. Then we have to go this way if we want to keep the enclosed region to our left. Now that may seem counterintuitive since we're going in a clockwise fashion, but you have to keep the enclosed region to your left. If your left arm is pointing out, as you walk around, it has to point into the region. When we get back to where we started at that little inner hole there, we'll go back out along the original cut. The integrals along each of those little paths will cancel out. And then we'll just keep on going around, just like normal, all the way around the boundary curve to where we began. In this way, Green's theorem will require that you integrate with the correct orientation around the one boundary curve and then the correct orientation around the inner boundary curve as well, always keeping the enclosed region to your left as you're walking around either of these boundary curves. Green's theorem will still hold in this case. These regions are not simply connected, we call them multiply connected. if the boundary consists of finitely many closed simple curves. Then the region is called multiply connected. Here's our example. We want to verify Green's theorem. The integral will be the integral around the boundary of R of 2xy dx plus x squared plus 2x dy, and the region is going to be an annulus, two concentric circles, the region between two concentric circles, the inner one of radius 1 and the outer one of radius 3. So let's verify Green's theorem. We'll always start by stating Green's theorem. The integral about the boundary of the region of m dx plus n dy is the integral around the region of dn dx minus dm dy, all times the element of area, dA. We'll begin by calculating that right-hand side. dn dx is 2x plus 2 minus dm dy, which is 2x, all times the element of area. Since the 2x's cancel, we're just integrating 2. We get twice the area. We'll get twice pi 3 squared minus pi 1 squared. That's 9 pi minus pi. It's 8 pi times 2. That's 16 pi. Now let's try the left-hand side. For the left-hand side, we have two curves. We have curve 1, which we will orient going counterclockwise, and curve 2, which, to keep the region enclosed on our left-hand side, we'll have to orient in a clockwise direction. So curve 1 will be r of t equals 3 cosine t, 3 sine t, where t will go from 0 to 2 pi. And for curve 2, we'll have r of t equals sine t cosine t, where t goes from 0 to 2 pi. The integral on C1 will be the integral from 0 to 2 pi. Remember, we were integrating 2xy dx plus x squared plus 2x dy. So we will have 2x y times dx. dx is minus 3 sine dt plus x squared plus 2 times x times dy. dy is 3 cosine dt. We get certain things can be factored out. First of all, a 3 from this grouping, and together with this other 3 will give us a 9. We can take a 9 out of the first grouping as well. So we'll have 9 times the integral from 0 to 2 pi. We'll have 6 minus 6 cosine times sine squared. The dt will factor out. We'll also have plus 3 cosine cubed, and then plus 2 cosine squared, all times dt. If you integrate cosine cubed on the entire period 0 to 2 pi, What is the effect of that power 3? If you take, say, 1/2 and cube it, you get 1/8. It brings numbers between 0 and 1 closer to 0. But 1 is still going to be 1 when cubed. So you get something very similar to the cosine curve, but the area is still going to add up to 0. That won't happen for this last term. What happens for the first term? U equals sine t, so that du is cosine t dt. If you do that, you'll have 9 times the integral from dot to dot of -6u squared du. And then we still have this plus 2 times 1/2 times 1 plus the cosine of 2t, all times dt. This very last term, of course, has an integral of 0 since you're integrating over 2 periods. This first term will give 9 times -6 u cubed over 3, but remember what u was. Then we'll have 1 integrated from 0 to 2 pi, which gives us 2 pi. On this first term, we have 9 times -2 sine of t cubed evaluated from 0 to 2 pi plus 2 pi. The sine of 2 pi is 0, the sine of 0 is 0, this whole term contributes nothing, and so far we have 18 pi. I'll put that in a bucket and hold it off until we calculate the integral on C1. Now we have to calculate the integral on C2. You'll remember that on C2, r of t was sine t cosine t, putting the sine first in order to get the orientation going in a clockwise fashion. We'll have the integral from 0 to 2 pi of 2 cosine. We'll have 2x, that's 2 times sine in this case, times y, which is cosine, times dx. dx in this case is cosine dt. X squared is sine squared, plus 2 times sine, all times dy. dy is minus sine dt. Let's see how these come together. When we distribute the sine, we'll end up with a sine cubed here. Just like before, if you integrate sine cubed, you'll get a positive bump and a negative bump that cancels out. So this term contributes nothing. Similarly, this other term contributes nothing. We can do the u sub there too. You'll end up with cosine cubed, evaluated at 2 pi, 1/3, minus evaluated at 0, 1/3, 1/3 minus 1/3, you get 0. The only part that will contribute anything is the minus 2 sine squared. But sine squared is 1/2 1 minus cosine of 2t by the half angle identity. The 2's here cancel, and the integral of the cosine of 2t contributes nothing. We're integrating 1 on an interval of length 2 pi. That's 2 pi, but with a minus. We deduce then, integrating on C1 plus the integral on C2, that you get 18 pi minus 2 pi, or 16 pi, just as on the other side of Green's theorem. This is a verification that the path integral and the area integral on Green's theorem give you the same answer. In our last lecture, we showed how the area in some region R can be calculated as 1/2 times the integral around the boundary of the region, x dy minus y dx. We can verify this completely now using Green's theorem. you'll have 1/2 times the integral over r according to Green's theorem. Now when you take the derivative on the first term, you have to take the derivative with respect to the other variable besides the one in the differential, with respect to x, so that you get a dx wedge dy. That'll be 1 times dx wedge dy. On the next term, you have to take the derivative with respect to y, but when you do, you'll get a dy wedge dx. You can reverse the order, but the price you pay is you change the sign. So we end up with 2 of these terms, which cancels with the 1/2 out front. So we're just integrating dx wedge dy, which gives us the area. I want to talk about conservation of energy. Let's let F be a conservative vector field. That means that F is a gradient of some scalar potential. Now in physics, they use minus P instead of F. P is going to be the potential energy. So this will be minus the gradient of some potential energy function, like this. Now, the work done by this force in moving a particle along some path c is going to be the integral of f dot dr. If dr is an infinitesimal displacement, then a little element of work would be force dot the infinitesimal displacement. If you add that up along the curve, you get the total work done. If we were to parameterize this curve and evaluate this path integral, we'd integrate from some t0 to t final of f evaluated on the curve times dr dt times dt. According to Newton, force is mass times acceleration. What we have here then is the total work done is the integral from t0 to t final, mass times dv dt, dotted with v times dt. Let's think about that for a minute. If we take the derivative with respect to t of v dot v, the Leibniz rule would give you dv dt dot v plus v dot dv dt, and that's twice dv dt dot v. What we have here on the left is the derivative with respect to time of the norm of v squared. So multiplying by 1/2 on both sides of this equation, we'll have the integral from t0 to t final of m over 2 times the derivative with respect to time of the norm of v dt. If we assume that the mass is constant, which we'll do here, then the integral of the derivative will cancel each other out. And what we'll have is 1/2 m times the norm of velocity squared evaluated from t0 to t final. Now 1/2 m times the norm of velocity squared is the kinetic energy. When we evaluate at t final, we'll get the kinetic energy final, and when we subtract and evaluate at t0, we'll get the kinetic energy initial. So by integrating f dot dr, the work, we ended up with the difference between the final kinetic energy and the initial kinetic energy. But there's another way to look at this because we assumed that this vector field is conservative. You'll recall from the fundamental theorem of line integrals that if f is some gradient of a potential, then the integral will be the potential evaluated at the final point minus the potential evaluated at the initial point. But in physics, F is minus P, where P is the potential energy. So what we'll have here is minus the potential energy at the final point minus the potential energy at the initial point. In other words, minus potential final plus potential initial. But we've also seen that this work is equal to the kinetic energy final minus the kinetic energy initial. Let's rearrange this equation. Moving the final terms together and the initial terms together, we get potential plus kinetic energy initial equals potential plus kinetic energy final. In other words, the total initial energy is equal to the total final energy, and that is what we mean by conservation of energy. In our next example, we're going to integrate around the boundary of some region of arctangent of x plus y squared dx plus e to the y minus x squared dy. The region is going to be a half annulus between 1 and 2. It looks like this will be a real mess to integrate around the boundary. We'll have 1, 2, 3, 4 pieces of boundary curve. Rather than parameterizing those 4 pieces, maybe it's better to use an area integral, and we can do that by Green's theorem. Besides, who wants to integrate something involving arctangent? So we'll apply Green's theorem and calculate an area integral over the entire region R instead. For Green's theorem, we have to calculate the derivative with n with respect to x. That's going to be minus 2x. And then we have to subtract the integral of m with respect to y. That's minus 2y. Now, one of these terms will contribute exactly nothing. If you're adding up x's over a region that's symmetric through the y-axis, you'll have just as many negative x's as positive x's. This first term will contribute nothing. The second term will contribute something because all of the y values in this region are going to be non-negative. The coordinate system that we choose to use will be polar coordinates. Theta will go from 0 to pi, not 2 pi, just to pi. The radius will go from 1 to 2. We're integrating minus 2y. Y is r sine theta, and then the area element is r dr d theta. By Fubini's theorem, we can integrate with respect to theta first. If you integrate sine from 0 to pi, you get one bump, and one bump gives you 2. We'll bring this negative 2 out, and then we're integrating r squared. That's going to be r cubed over 3. You can see that we did both integrals at once. We'll have this negative 4/3, and then 8 minus 1. 7 times 4 will have negative 28/3. Remember, Green's theorem has 3 forms, and one of those forms is the flux form. Let's suppose that we're dealing with some region in the plane, and we have a fluid The fluid has a density and a particle velocity. Let's think about what we get on the boundary when we multiply the momentum density, rho v, dotted with the normal vector. That's the rate at which momentum should be pumped across the boundary. What do we get when we integrate around the boundary of R, rho v dot n ds? Let's think about the units of this answer. Rho has units of kilograms per, well, we are in the plane, kilograms per square meter. V has units of meters per second. N has been normalized and hence has no units. The element of arc length has units of meters. The units that are left over are kilograms per second. What we get is the rate at which mass is exiting the region. This is called the mass flux. The units of mass flux are kilograms per second. But there's another way of calculating mass flux that's independent of this. You recall that the total mass in a region is the integral over the region of density times the element of area. This will have units of kilograms. If we take the derivative of m with respect to t, we don't get the mass flux. This is the rate at which mass is increasing in the region, the rate at which it's going in. It's the opposite of the mass flux. Now, let's play with this equation a little bit more. We'll apply Green's theorem to the right-hand side. We get minus the integral over r of the divergence of the momentum density times dA. On the left-hand side, we'll bring the derivative into the integral and get the derivative of the density with respect to time, but this time it's a partial derivative. If rho is a function of x, y, and t, time, and we integrate out x and y, we end up something that only depends upon t. So an ordinary derivative is appropriate here. But when we bring it inside, rho is still a function of x, y, and t. So there we must use a partial derivative. We'll now combine these two integrals, which are of the same kind. They're both area integrals now. We'll get 0 is the integral on r of the rho dt plus the divergence of rho v dA. To get to this point, we had to actually make an implicit assumption that the only way mass could change within the region R is by flux through the boundary. If mass is either created or destroyed within the region by some other means, you would not get 0 here. You would get some other source function. But if you assume conservation of mass, the only way mass can change within the region R is by flux through the boundary, and you would end up with this equation. This equation will represent conservation of mass, but we're going to take one more step. We're going to first of all assume that the integrand here is continuous. Also, keep in mind that this equation should be true no matter what region R you're dealing with. If this integrand were non-zero at some value, by continuity it would have to be non-zero for nearby points, and you could choose the region R nearby to make sure that the function would continue to be positive. If that's the case, then the integral can't be 0. We deduce then by something called the vanishing integrals principle, that if the integrand is continuous, and if you get 0 for all regions R, then the integrand itself must be 0. This is called the vanishing integrals principle that we used. And this equation is called the continuity equation. The continuity equation represents conservation of mass. The continuity equation is one of the equations of fluid dynamics. It turns out that the dynamics of a fluid is completely determined by equations that represent conservation of mass, conservation of energy, and conservation of momentum. I intend to investigate the continuity equation further in a lab.